All right, so in this video, I guess, Lee, we're going to be wrapping up pretty much the random numbers section because you've pretty much got what you want, right?
Yeah, we've pretty much gone through, well, not pretty much, we have gone through all the three hashes that I wanted to do. A real pseudo-random number generator that has a few overloads with it, so we've got different options for pulling numbers from it. But I wanted to go one last time through and do another look at the comparison, so we can compare the standard built-in random generator
Okay.
with our final one, as well as some of our hashes, and look at the speeds and stuff that we got.
Okay.
So if we go in, let's get our benchmark to start with. So I think let's go with whatever we get with 1,000. If I remember right, that's 4 million different iterations. So we build that. So this is our standard built-in at 4 million iterations. So if I take this information and I mark it, and if I remember right, you've got Notepad open for me over here.
I do.
So let's call this one, this is the standard. So we'll put our numbers in there. Now, let's compare that with our 1D hash. And in this case, yeah, we can leave it with the multiply to make sure that I want to do, yeah, no, let's keep it fair. So I'm going to create another counter. So count equals 0 here. Put a count there, because otherwise it's really not fair. Well, technically I could just do iterations. It does the same thing. There. I don't have to create another variable. What I want to do is just make sure that the hash gives us an accurate number without having to worry about the x and y. So if I build this and we bring up Notepad and do some comparisons. So speed-wise, built-in's faster for the same iterations, not much. But with this one, we get a much closer approximation to both 0 and 1. Our spread looks like...
The spread's better. I mean, just looking at the mean, I mean...
Yep, and we're... Well,
yeah, it's pretty...
the average, this average is closer.
Yeah, because 003, that's 999. Yeah.
Yep. And then if we look at the duplicates, it's really, really close. So both have their trade good and bad points. Now the thing that you got to remember though is this one, the one we just ran here, is a hash. It's not a real number generator, which means that you're going to get the same number every time you enter in a number. The only reason why we got these numbers is because we incremented on an index that isn't repeating.
So go ahead and copy that. Paste that one over in Notepad up underneath the last one.
So if we go ahead and hit mark, it'd be kind of nice if there was a hotkey to mark that. So this is our hash D.
Okay. Let me do this for you real quick.
Yeah.
I'm just going to go ahead and give us a little more. All right.
All right. So now let's look at our hash 2D. And already this one's taking longer.
Yeah, a lot longer.
Yep. Now, let's do the same thing, copy it. Edit. Oops. I can work a mouse, really. All right. Now let's bring up Notepad. And still, if we just do a real quick comparison, it's much, much slower. We're still getting really good representation, a real good distribution, really close to mean. A lot of duplicates though. But
Yeah.
that is kind of expected considering the fact that we are generating based off of a number that is coming real close to repeating because we're using whole numbers and we're using y, which is repeating every single time we hit x. So every time x goes up by 1, every y value is repeating. So it doesn't surprise me that we have a lot of repeating values in here, which is something that we have to just accept when you have a hash.
Mm-hmm.
So we can put this one over here. Has. He has 2D.
H on the other side.
Yeah, I'm
Sweet.
working on it. Now it's Haas. Yeah, he has 2D, and he's apparently Dutch or something. No offense if that's a bad word in Dutch or something. I have no clue.
Didn't you already copy that, or was I seeing things?
Mm, I hope so. No. Apparently it went bye-bye.
Okay.
Wow. I think edit, mark, select the whole thing, hit enter, come over here. There we go. I was like, oh, that was fun. All right, so that gives us our 1D, our 2D. Now let's look at our 3D. And this will probably take even longer. Yep, and it did. But we got a lot less duplicates out of it. But that's also because what we are generating our hash off of is a much more, not much more, it just has an additional value to mess with. And we're using that multiply by 0.1 to get us a fraction. So with all of our hashes, though, they're really good at getting you information or a unique number for a set input.
Mm-hmm.
So that's their strong point. This is not something that you would want to do, well, let's say, as the foundation of a a value type noise, and we'll see why later, that you wanted to run in real time.
Mm-hmm.
If you were trying to do, say, 4 million iterations of this, and that's really not that hard when you think about it. If we bring up the calculator real quick, it's around here somewhere. Is
Hang
it?
on. No, it's hang on one
Oh,
sec.
it fell off.
Yeah, it has. There you go.
Okay. Now, the reason why these numbers become important when you start looking at it is a 1024 texture.
Are you on mine? There you go.
Apparently, numlock was off too.
Ah.
So 1024 by 1024, you're at already over 1 million. So if that's a very common texture size that you would use, or that you could use inside of, oh, say, a game for some reason.
Mm-hmm.
But just a 1K texture is already at 1/4 of this. So our hash 3D, if we're to take, let's clear this. So effectively 8 seconds, or just right around 8 seconds for 1 million is a 2-second delay. For a game where you're wanting to push 60, 100, or more frames a second, any operation that's going to take 2 seconds is not something you want to do in real time. And definitely not something you want to try to do in the update cycle of a Unity script.
Right.
This would be something that you either did at level load, at some sort of intermission, or and offloaded as a thread and signaled the code when it was ready. So definitely not high performance, but it does give you a unique number for its given inputs every single time, so that you get the same numbers no matter what, which is why we need one and why we built it. All right, so I do have that one copied, Jess.
Mm-hmm.
So now we get into our nice little well 512. Now if we run this guy, again, 4 million operations, still not blazingly fast, but compared to everything else, not bad. So if edit mark. Now if we look at that compared to our first one, which was under a second, so
But just under a second.
yeah, just under a second, and this is just over a second. So very, very close. But we also get no duplicated information whatsoever compared to the 3600 plus that we get with the built-in method. And again, deterministic, meaning that we give it a seed, we'll get the same numbers every single time. The main benefit that we get, and the reason we want to do this type of random number as opposed to the one that's in the build, is that by doing this, we're guaranteed that every platform that uses this implementation that we wrote will perform exactly the same. We give it the same number. It doesn't matter if it's PC, Mac, web, a mobile app. This will generate the same numbers every single time for every platform, which is a huge benefit for us.
Yeah, and I don't really think we need to test the other ones. I mean,
Well, I want to test one of them.
Okay, okay. Well, hopefully the double min max.
Yeah.
Okay.
The most complicated one. Well, that's
Well,
the
just
one that
keeping
doesn't
everything
really.
in doubles.
Yeah. Just to keep it. But I want to see how much performance hit what we incur from using the range function.
Okay.
Oops. Apparently I was still running. Shift F5 if you don't already know it. We'll cancel anything that you're running. And we'll uncomment that. All right, so because this should add some time to it. It does. Not a huge amount, but it does add some time to it. So if we compare that with our last run, which was right here, we've added, 132 milliseconds to our overall run by casting it into a range of addresses. So we don't need to copy that in.
Yeah. Because this is, I mean, we're pretty much at the end of the video now. So is there anything else you want to say about this?
No, it was pretty much what I wanted to do was just have a comparison all at once, because we've scattered them throughout the videos. But this gives us just a good look that we can compare against where we started, where we ended up,
Right.
and the benefits of each, and why we would want to use these different types of, why would we want to use the hash, why we'd want to use the well 512. And when we get into our next set of videos, which is when we start undertaking noise, the cool thing is these hashes that we've done, these are literally kind of our basis of a random number generator, or our first noise.
Gotcha.
When you think about it, this hash 3D literally is a very non-robust type of noise, because it will give us a texture that we could throw in and assign to gray, throw it in a color, put it into a texture 2D, and it's effectively white noise.
Mm-hmm.
where hash 2D gives us a 2D noise. Hash 1D is something that you could use if you wanted to feed into some sort of animation curve to put a little bit of noise into, say, the motion of an object
Mm-hmm.
or the walking path of an enemy. You could use these. They're not smooth, they're very rough, but if you wanted that, we could do it. We're going to get into some more advanced noises, which we can get into smoothing and lots of fun stuff that we can play with. But we won't get into any 1D noise other than this hash 1D if you wanted random numbers.
Okay. So is that pretty much everything then for this little series?
Yep.
Awesome. Well, thank you very much, Lee, and everyone else for joining in. And that concludes Random Numbers. Thanks a lot.